Here we have some worked solutions to the written assessment 2 from last year. So this written assessment, it's not a perfect sample. I mean, it's giving you an idea of the length, the layout, some idea of the difficulty, but you can kind of get different questions. So, for example, some questions might have been on this that I wanted to ask in written assessment 1 but didn't. So basically, you can't really say much. I think the 40% written information on Canvas gives you a bit of a hint as to what is coming up. So I have worked solutions here, and we've had a big sorry story about this, so we'll just get into this. So Maclaurin series. So the Maclaurin series is basically how you can write a function as an infinite series, and if you take some of the terms, in this case 4 of them, you get an approximation. And we're going to see here how good this approximation really is. And in this question we will actually test that. So all this requires is calculation of some derivatives evaluated at 0. So we differentiated, we put in x equals 0 into log, got log 1, that was 0, that was no problem. The differentiation of log of 1 plus x, strictly speaking, doesn't need chain rule, because if you forget to use the chain rule, you'll be okay, but still here I do it. So the way I kind of do it is I say, oh, you got the outside and the inside, and the chain rule says differentiate the outside. So I've differentiated the outside function here is log of x, derivative log of x is 1 over x, and what I did is I evaluated at the inside. And then you multiply by the derivative of what's inside, and the derivative what's inside is 1 plus x, and derivative of 1 plus x is just 1. So you multiply by 1. So if you forgot that, it wouldn't have made no difference. Now you'll want to differentiate 1 over 1 plus x again, and you can do this using the quotient rule, but it actually makes more sense to write it as divided by 1 plus x once, in other words, to the power of minus 1, and then use the chain rule repeatedly. Now again, if you forget to multiply by the derivative of what's inside, it'll be okay, but this is probably the way to go. So anyway, evaluating these at 0. So I differentiated 1 plus x to the power of minus 1. That should be okay for y. So I guess the only thing then is when I'm differentiating this, to fix the minus, you can just write down a minus, but you could also remember that maybe I'll just pick a different color here to do some writing. Green, yeah, something like this. Yeah, happy days. So fixing the minus 1 is one way of dealing with that. Okay, and off you go. You evaluate at 0, and then you sub in these different derivatives. You got this one, this one, this one, and this one. Just sub all those numbers in, and then you can tidy this thing up. Then the next part of the question is use it to approximate log 1.1. Now, a little bit of friendliness there, where it writes the log as 1 plus 0.1. And so what you have here is you're talking about x equal to 0.1. So just sub in x equal to 0.1 into the Maclaurin series here. So we do that, and I get 0.095333. And then it then says the exact value to 5 significant figures. It gives it to us, and then calculate the percentage error. So to calculate a percentage error, you do the error, the difference between the approximation and the true value, and then you divide it by the exact or the true value. And it came out to be this number, and convert, multiply by 100%. So actually, I think there's actually a little mistake here which we can correct. This is, I'm not sure exactly, I probably forgot this 0 as my guess, but this is 0.30, 1, 2, 3, 2, which is 0.02%. So that was wrong. Okay, so that's that. Next question is a theoretical question. The three-term Taylor method has a similar error profile to Hines method. What is the disadvantage? I think we saw this in the first thing. The three-term Taylor method requires differentiation. And if the derivative depends on y as well as x, or possibly just y, then you'll need implicit differentiation. So that is the disadvantage. It might be easier to read the the answer. It says three-term Taylor method requires differentiation, and in fact, implicit differentiation if the derivative depends on y. Okay. Right. Another question here. The four-term Taylor method approximates solutions of ordinary differential equations. It uses this approximation. So in other words, it's not quite the Maclaurin series because it's close to x equal to x0 rather than close to x equal to 0 where it's good, but it's the same kind of idea. And what this thing is, if you multiply this out, you will get an x cubed. And so this thing here is a cubic. In other words, got an x cubed in it, and it is the best fit in the sense that at the point x0, it goes through the curve. It has the same slope. It has the same second derivative, same third derivative, and in that sense, I think you could probably say a little bit more. So it's the best cubic approximation to the curve. So the answer there is tangent cubic. Right. Another question here. Okay, so this one, you have information about the solution at two different points. So this is a boundary value problem. So this makes it a boundary value problem. The first thing then, most important, and is to write as two first order initial value problems. So here you'll notice that you have m at two different points. This is like the initial, and then this is like the final value of m, and that's what you're trying to hit. Now, if you don't write this as two first order initial value problems, you're going absolutely nowhere. You're doing very, very poorly. So what you want to do is always to let the first derivative be a variable called v. Now, in context, a v might mean something. So if x, say if it was dx dt, and x was displacement, v would be velocity. In this context, the first derivative, dm dx equal to v, actually makes sense as well because it's what's called the shear force. So you introduce this new variable v, which is equal to the first derivative, and then you differentiate both sides with respect to x, and then you should be in good nick. If the differential equation is a bit more complicated, you can write the differential equation in terms of v, but here, not really necessary. You have that the second derivative of m is dv dx. So you can just replace that second derivative with dv dx, which is what we did below. And dm dx is the slope, it says slope m, slope of m, and dv dx is the slope of v. And if you have two slopes, you're going to have two Euler methods. The initial m is equal to 0, we have that, and we do not know the initial v. So this is our problem, and we're doing the shooting point method, shooting method. I don't know where this point comes from. Shooting method. Now you're trying to go, the picture on the right here is just saying you're trying to go from at x equals 0, m equals 0, to at x equals to 6, m equals to 6, and you don't know the initial slope, and the obvious thing is to just shoot straight at it with a slope of 0, but actually you can come up with whatever you want. So that's what we're going to try first. So VA is the first slope that we try, and it's 0. Now this question, you've got a rod of length 6. So you get x equal to 0, x equal to 6, and it's chopped into 4 pieces, each of length 1.5. And the temperature, or sorry, what am I talking temperature? It's not even a rod, it's a beam, sorry. So m is equal to 0 here, and what you'd call this is m1, m2, and m3 if you were using Euler's method. And then this would be, well, you're trying to hit 0 here. So that's what these m1s and m2s and m3s. So we have to go down to what we could call m4. So this is what this table is kind of telling us, that we have the initial situation, we've guessed v equals 0, and we need to do 1, 2, 3, 4 steps of Euler's method. And there's 2 slopes, so we need 2 Euler methods. So here you see the first 2 Euler methods, and notice how do they work? Well, both the previous values were 0, so they're both equal. The previous value is 0, both same step size, And then the slope of m is v. So this here is actually the previous v. I might call it v0, for example. And then this is the previous dv dx. And notice, because it's the previous, it uses the previous x. So these approximations, by the way, are for x equal 1.5. There's a step size of 1.5 here. And if it is the previous dv dx, and the dv dx depends on x, you must use the previous x, which we did. Okay, so that's those numbers. Then we go again. The previous m is 0. The previous v I should say is minus 15. And now this is the previous v. This here is v1. And this is the previous dv dx. And just note that it uses the previous x. So this is at this point, and what's the previous x? 1.5. And we get the numbers out. We go again. Again, the previous m was minus 22.5. Previous v is minus 16.58. And plus step size. And then this minus 16.581 is actually the previous v, which is v2. And again, this is using the previous x, so this is corresponding to x equal to 4.5. So if we're using previous slope, we use previous x. And then we get one final shot. Now, we're trying to hit 0, and we got minus 72.246. That's a massive undershot. So we'll try a larger slope. It doesn't really matter. I mean, if you do 5, 1, 2, I just went with 10, I think, below. A nice page break for us. Did I go with 10? Oh, yeah, it's down the very bottom. Sorry, this doesn't come out great. So we try, it's not written here, it's written up the top. Let's try with a slope of 10. So we do the same thing, go back to the very start and do a slope of 10. So again, this is at x equal to 1.5, x equal to 3, x equal to 4.5. So I'll say this, and then finally this is at x equal to 6. And so this actually is another undershot. And it doesn't actually matter if you get an undershot. So now you've got two shots. With a slope of 0, you've got an undershot. And with a slope of 10, you've got an undershot. So we're going to need a slope bigger than 10 to hit it. And we use this formula here, which will be given to you in the written assessment. So VA was 0. Yeah, y of xf, this is what we're trying to hit. This is what we're trying to hit. And we're trying to hit was at x equal to 6, the bending moment of 0. So we get out 12.041, and then we take our final shot. So I did 1.5, we did a 3, and we did 4.5. That's all the question I think asked for. If we go back, maybe we'll just check this. The question wanted, what's going on at these points? So we calculated them, but we can check our answer. So with that slope that we calculated, it should be the one that makes us hit 0. And if we just go a little bit further, you can see that you basically get 0 up to around here. Okay, here's another theory question. Okay, unfortunately, it's been cut. We've been really hurt with this recording fiasco. I might even possibly change tack here. Yeah, I've just gone to a different program now. It'll work better with the page breaks. Okay, so this question, use finite differences to show that Laplace's equation. Now we might just write down here, what does this is, t is steady state, where you have some kind of boundary conditions. So the boundary conditions will be some function of x and y. So it might look like, how do we write down? So basically you know what's going on the boundaries. In theory, they can be very complicated, but let's see. So in theory, you have the boundary conditions. So the temperature is known. The way you write the boundary, that outside is you actually this partial derivative. So I guess we have a rectangle. So the boundary of the rectangle to, I suppose, real numbers, and it might be given as t of xy equal to some function of x and y. So you do know what's going on in the boundaries. And then the question is, for that Everything else is insulated, so the top and the bottom is insulated. So if you imagine setting your plate up with some initial temperature, say 0, and putting it in contact with these boundary temperatures, these heat sources and sinks, and allowing enough time, it'll eventually reach equilibrium at steady state, and the steady state temperature will satisfy this partial differential equation, Laplace's equation. Okay, so what we want to do here is use finite differences to show that we're going to approximate the partial differential equation using finite differences, and we're going to show that basically that any solution of that, the thing that when we do the finite differences, it satisfies the mean value property, that the temperature is the mean or the average of the temperature at adjacent nodes on a square mesh thin plate. So square meshed means that the plate is meshed into squares. That picture on the right is not in squares, but it should be. So delta x equal to delta y. That should be written somewhere. Yeah, it's kind of written, it's assumed down there, but we're taking that these two are equal as distances. And the finite differences that will be on the exam paper is given this formula here on the left. So this says that the second derivative at a point is approximated by this. So the y of xi plus 1 means the next value of the function. Now the function for us here, the role of y is being played by temperature, but the role of x is being played both by x and y separately, because we have two second derivatives. So xi plus 1 means the next point in the x direction, and y of xi plus 1 means the next value of the y. So at the next point over in terms of x, the value of y. In our context, the temperature at the next point over in terms of x. Minus twice the current, for us in context temperature, plus the previous temperature. So we set up a point, a generic point, that's this diagram now on the right of your screen, that just represents some point in the grid, some internal grid point. Every single internal grid point there has 4 neighbors. What I'm calling TU, which is the temperature up, TD is the temperature down, TL the temperature to the left, and TR the temperature to the right. All of them have that. And so what we have, TR is the next temperature with respect to x, TL be the previous temperature with respect to x, if you kind of assume this kind of axis. And similarly, TU is the next temperature with respect to y, and TD is the previous temperature with respect to y. And so if we want to approximate the partial derivatives using the formula above, look what we have here. So this is the next temperature with respect to x, minus twice the current temperature. So we are approximating this partial differential equation at this point here. So we're at this point here, okay? So the current temperature is T, and the previous temperature with respect to x is TL. And then similarly, with respect to the y direction, and we divide by delta x squared, with respect to the y direction, the next temperature is T up, the current is still T, and the previous temperature with respect to y is T down. And then what you do is you multiply both sides by delta x squared, and if delta y is equal to delta x, multiplying by delta y, delta x. So basically I multiply, look what I'm saying here. So I'm multiplying a sum, so they both get multiplied by a. And I'm saying that when I multiply the first term by delta x squared, obviously that gets rid of the division by delta x all squared. And when I multiply the second term, well, you've got a division by delta y squared. You're multiplying by delta x squared, which wouldn't get rid of it, but in fact delta x is equal to delta y. So if I've multiplied by delta x squared, I've in fact multiplied by delta y squared, which will get rid of it. And then from here, it's just a simple case of solving for big T. And we have shown that the temperature is indeed the mean of the adjacents. Adjacent. Okay, another question now, Fourier's law. So here again, this is just a snapshot of the plate. It's actually not a million miles from the picture on the top right of your screen. You've got some current point, which is where the 52 is, and you've got, you know, an up temperature, a down temperature, a right temperature, a left temperature. The temperatures in the corners in this calculation don't play so much of a role. And what you want to do is you want to calculate this vector. So the vector is basically giving the direction of the heat flow. I guess the direction to us is probably a bit more interesting than the magnitude, because we don't really have a great feeling for the numbers. But anyway, so what we want to do here is this vector is given in terms of partial derivatives. It's on the screen there. And we want to approximate those partial derivatives. Now what you could do, and it would be reasonable, would be to take, for example, just look at these two. So the partial derivative in the x direction, just do kind of a rise over a run. So you get like 62 minus 52 divided by delta x, and the delta x is 0.2. And that, to me, looks like 50. Now, that's fine, but you can actually, it's possible to also take into account the 36. And if in fact you do the two of those, so in other words, also work with 52, and so do 52 minus 36 over 0.2, you get another answer. And if you average those two answers, you get what's called the central finite difference. And that's worth doing. In this case, it's going to be a little bit more accurate, because you want to take into account what's the temperature difference on the right and the temperature difference on the left. And that's where this central finite difference comes in. So rather than, like, so the thing we wrote under reasonable is kind of next minus current. We also mentioned something like current minus previous. It's good, but this is another alternative to not bring current into it at all. Do next minus previous. Now the only difference here is the distance between them will be 2 delta x. So this is the same as doing the two reasonable ones averaged. You can get this one. It'll give you a better answer. So we do, rather than 62 minus 52, we do the next minus the previous. The 36 minus the 62 minus the 36. So that's next minus previous, written below, divided by, and the distance between them now is 2 delta x, because you're going there's two meshings as such to go over. So maybe that's easier to look here. Like to go from temperature L to temperature R, you're doing 2 delta x's. Okay, so that's where the division by 2 delta x's. So you estimate both of them using this thing, and then you just use the formula where you multiply by minus k dashed. So that's what we're doing over here. Calculate this vector, and it is a vector, it's two numbers, so if you want you can do i's and j's, and then you can kind of check your answer. That's going a little bit more down, because the minus 18.7 or whatever is a little bit bigger than the minus 15.7. They're both going back in terms of x, back in terms of y, but slightly less than, slightly steeper than, well, not quite 45 degrees. So that's where this green arrow on the grid is going. So that's the direction of heat, and your answer should make sense. So you're going from hot to cold when you go right to left and up to down. Okay. Oh, this question. So right, we've got the transient state temperature and insulated rod. So hopefully we have a rod somewhere. Actually don't, we might draw this. So you got a rod of length L, and you have some boundary conditions. So the temperature here is temperature 0. I might actually put the temperature or the length somewhere else. My apologies. So you got x equal to 0 here and L here. You got temperature 0 on the left, and that is for all possible times. And then the temperature on the right at x equal to L is TL. It's a bad name for it, but anyway, for all possible times. And then what's happening is the temperature in the middle, say at a distance x, it depends on x and time. So we've got a scenario where the temperature is increasing. Now you have a temperature distribution at time 0. This is like the initial temperature of the rod. But what happens is it's insulated along the rod, so the air doesn't come into it. It's going to potentially heat up or cool down, or some bits will heat up and some bits will cool down. And what you're talking about is it gets closer and closer to the steady state temperature, and the temperature at each point and time satisfies the heat equation. Okay, so that's the kind of setup here. So consider a point I times delta x. So what does this delta x, delta t means? It means you're chopping the rod into delta x's. So you can imagine chopping this into delta x's. So for example, into 4 pieces, something like that. So you got 1 delta x. This is a distance 2 delta x, a distance 3 delta x. This is L and this is 0, and so in this case delta x is the total length divided by 4, or you could chop it up finer. And you're also chopping up the time. Now it's asking us to take a point in the domain, so we'll see what the domain looks like. We can do, well, I guess this is, if you haven't seen the lecture video for the heat equation, you'll have to go and have a look at it to understand what we're doing here. So what we have to do is we are saying, and hopefully it's written somewhere. No, it's not. I don't want to give the whole lecture, but this TIL for us is approximating the temperature at the point I delta x. So I delta x is along the rod at a time L delta t. So delta t is the time intervals. It's like the step size for time. So we got step size for distance and step size for time. And we want to show that if we rewrite the heat equation up the top of the page using finite differences, what is the equation we get? And it looks like this. So this is kind of this L plus 1 kind of signifies next time. L means previous time. And the lambda is kind of like a step size, and the function there is, it's not really a function, just a formula, is kind of like a derivative, but not quite. So this is the setup that you want. So you have the rod down the bottom with the temperature, the point we're looking at, and it's a point in distance, that's the I, and a point in time, that's the L. And what we want to do is we want to look at the same time 3 points on the rod. And of course, you want, if this is the current, if you go 1 over, that's I plus 1. It means the next distance, next temperature and distance, and then the previous temperature and distance. And we also want the same point on the rod, but at the next time. So these are this is our schematic that we need. And so if we set this up, so we have this axis here on the right. So the x-axis is the horizontal and the t-axis is the vertical. Okay. Let's go to, okay. So what we want to do, and these partial, the finite differences are, well, this one we've seen a bit earlier. So we'll go up to it there. This yoke, the next. So second derivative is approximately the next minus twice the current plus the previous. And we'll probably write down the other one that we're doing. The other one is a bit easier. So you can approximate a first derivative with you can approximate a first derivative. The formula is basically that dy dx at a certain point xi is approximately y of xi plus 1 minus y of xi over delta x, and this here is the next. This here is the current because it's at xi. Okay, so this is what we're doing here. So look at this thing up here. So the second derivative we're looking at first. So the formula above says the next one over. from the current, and it's with respect to x. So the next one over with respect to x is this one. Minus twice the current plus the previous with respect to x, and this is the previous with respect to x. So that goes there. And notice it's a partial derivative, so it means time doesn't change. They're all on the same time, because a partial derivative is all the other variables are constant in particular time. Right, and the other one then, the next, but it's with respect to time. So the next with respect to time is this one, minus the current with respect to time is, well, this one. And then we divide not by delta x, because the distance here is delta t. That is the time step. The distances here are delta x's. And similarly, partial temperature, partial time, everything else should be constant, in particular distance. So these are at the same distance. Okay, and all you do from here is say multiply both sides by delta t. And this is just algebra really. And then if you want, you can pull out the delta x squared, and you've got k by delta t, and you call that thing lambda. And then all you want to do then is get rid of this, so add that to both sides, and you end up with the formula that kind of was asked for. What's part B? Theory question, very simple. Give a condition on lambda that guarantees that using the formula we just derived to approximate solutions are stable with good transient. So to be, now I think in the heat equation video there's a bit more on this, but basically the answer is just less than or equal to a quarter. And then we have another theory question. Explain why the steady state satisfies this. So it should be explained here. So the temperatures, when they go to a steady state, they go to a constant. So the temperature at each, initially, you know, they're heating up in the sense that the temperature is changing. But if you allow enough time to go, the temperatures are going to go to a constant. In other words, say one of them will get closer to 20 degrees. It's not going to change anymore. It's not going to change with respect to time. Its derivative with respect to time is going to be 0. And if the partial derivative with respect to time is 0, well, look at the equation up the top there on the left, that's circled in green. If the partial derivative temperature with respect to time is 0, the k times the second derivative is also going to be 0. And then the question is, how does this imply that it's a straight line? Well, in steady state, essentially, the temperature just depends on distance, because time is just not a factor, because they're not changing in time anymore. So basically, you're looking at what are things that have a second derivative of 0, and the answer is lines. And that's why, does it say, explain why it's straight line, because only straight lines have a 0 second derivative. Okay, so that was a theory question. And now more of a calculation question. So we have values of k, etc. We have initial conditions. This is x equal to 0. It's 30, and at x equals 0.8, this rod is only that long, is 90. Okay, and then the other initial temperatures are all 0. So this is at any point in between. Now we need to do part A first, mesh the rod into 4 equal pieces. We did that below. So we chop the length 0.8 into 4 pieces. You get 3 internal grid points, call them temperature 1, temperature 2, temperature 3. Their initial temperatures are all 0. So that's the thing below. Okay, mesh the rod into 4 equal pieces. We did that. Label appropriately. We did that. Using delta T equal to 0 and the equation derived in the previous question, find the transient state temperatures. So we find the lambda here and put in the k. The k is this yoke. And the delta t is 0.1, and the delta x here is the distance between these, 0.2. And we get that, in fact, it turns out, that looks a bit funny, doesn't it? How's that given 0.2? Looks, maybe it's just a coincidence. Oh yeah, it's because the 2 gives the 0.2 squared is 0.0. Okay, so we're using this formula here where the lambda is 0.2. So now all of these are previous in time. Okay, so when we use this formula, we go to the next time. So the very first time that we're talking about, L equal to 0, corresponds to time equal to 0 delta t, which is 0. And then L equal to 1, we're using a step size here. The question says a step size of delta t equal to 0.1. So L equal to, this bit doesn't make sense. L equal to 1 means t equal to 0.1, one step size. L equal to 2 is equal to t equal to 0.2. So that's all we've been asked to do. Now this, so here is a particular temperature. It could be temperature 1 or temperature 2 or temperature 3. And if you look at it, this is the same temperature. This is the temperature to, I'm just going to write to the right. This is the same one. And this is the temperature to the left. So I'll even annotate this a little bit more. So the previous, so you got all previous. So where you were before this, at time equal to 0.1, the initial setup looked like this. The temperature we had was 30, 90, and the initial temperatures were all zeros. They're not approximations. That's the genuine initial conditions that at any point x between 0 and 0.8 at time equal to 0, the temperature was 0. So this is the initial state, as it were, of the rod. Now, so this formula says use the previous. So the previous T1, T2, T3 were all 0. The step size, well, it's not really a step size, the lambda was 0.2. And then if you look over here, so this is temperature 1, remember? Well, I guess this is actually temperature 1, 0, temperature 2, 0, temperature 3, 0. 0 corresponding to initial time rather than 0 temperature. So if you look at T1, the temperature to the right is 0. That's that. Minus twice the current temperature, which is T1. And then the temperature to the left is 30. If you look at temperature 2, the temperatures to the right and left are both 0. And for temperature 3, you have that the temperature to the right is 90 and the temperature to the left is 0. So then after, at the next time, the temperatures are, this stays at 30, this stays at 90. I'll just do one significant figure for these. So this went to 6, this went to 0, and this went to, well, we can just write down 18. So again, we do over here the previous temperatures, T1, T2, T3 is 6, 0, 18. The lambda, and then the temperature to the right of temperature. So this here is temperature 1. To the right of it, you have 0, and to the left of it, you have 30. So here's 0 to the right, 30 to the left. Bang in the numbers. Then looking at T2, the temperature to the right and the left. And then finally temperature 3, the temperature to the right and the left. And then we're done. Okay, so that's how that works. And then find the limit as time goes to infinity of the temperatures. So these are not the approximations, by the way, but because our lambda is less than a quarter, as time goes bigger and bigger, we have stability, so we're going to get closer and closer to the steady state. So basically this question is asking about the steady state. Now the steady state is a straight line. It goes from 30 to 90, and it's y equal to mx plus c. So the rise over the run, you go from 30 to 90, the rise is 60, and the run is 0.8, you get a 75. And then if you mx plus c, it's just y equal to mx plus c. We just found the m is 75, and the c is where it cuts the y-axis, you get 30, so you get 75x plus 30. And then the final question last year, hence suppose the calculations were to be continued, what would be an appropriate stopping rule? As I said, because the lambda is less than a quarter, you will get closer and closer to the steady state. So if you were to sub in x equal to 0.2, 0.4, 0.6 into the steady state, you'd find that this, remember, the temperature here is temperature 1, the temperature here is temperature 2, temperature here is temperature 3. Temperature 1 will get close to 45, temperature 2 will get close to 60, temperature 3 will get close to 75. The suggestion in lab 8 is that you keep on going until the distance between those temperatures and the steady states get less than 0.5, and it should happen for all three of them, hence the and. Okay.